So we were going to talk about MRFM cantilever beam detection because it's my jam and I wanted to talk about it. But also I thought it would be a really good example of a second order measurement system. So that's what we're going to do. So in MRFM, the primary detector is a small cantilever beam with a magnetic tip. Model the beam as a spring mass damper system with mass of 6 picograms, spring constant of that, and damping coefficient of that. What is the natural frequency? What is the damping ratio? And free response, how long before the amplitude must be less than 10% of its initial value? An upper bound is sufficient. So, let's draw a little model over here of how we're going to do this. So first off, we've got a cantilevered beam with a little magnet on the tip from the side view. And we have this vertical motion goes up and down. Okay? Now, we're going to, you guys haven't had vibrations yet, so you haven't seen like the multimodal concept. Oh, a couple of you. But we can approximate this thing as having some mass that goes up and down at the tip. So we can just say that the motion is concentrated at the tip and it goes up and down. All the mass is concentrated there. And this beam acts a little bit like a spring, and then there is a little bit of damping that leaches energy from the system as well. So we could come up with a lumped parameter model for this, where we have a mass, and we have a spring, and we have a damper, which you guys, may or may not be familiar with seeing these sorts of lumped parameter elements. Probably are familiar with the mass and the spring from dynamics class, but the damper you may not be used to. That's okay. We could draw a free body diagram of this mass. So let's have our coordinate go this direction. We'll call it Y. And we could come up with free body diagram here. So we've got, I'm going to just make a claim here. If we say that Y is measured from equilibrium, where the spring is in equilibrium, and if it was at rest, it wouldn't move at all, we don't have to take into account gravity. I could prove that to you, but it would take me 5 minutes, and I don't want to. What I really mean is we don't have time in this class to get into that detail. This is sort of a sidebar analysis, so we're just going to sidebar that discussion. And I'll just claim that we don't need to worry about the gravitational force on this because it cancels if you make Y measured from the point of equilibrium. So we're left with a spring force, Fk, and a damping force, Fb. We all know that the force the spring exerts is K times the displacement from equilibrium. Yeah.
So the bar itself is not moving vertically at this moment. We're just modeling it. So like wouldn't the spring force and the damper force be the opposite direction too?
Yeah. So the way I do dynamics with the sign conventions is maybe a little bit different than you're used to. I always draw everything in the positive coordinate direction, and then I put a negative sign if it is going the other way. So if I was to move this mass up from equilibrium, the spring would pull down, and so the damper would pull down. And so I have to put a negative sign here. So Fk is equal to negative Ky. solution, the free response solution. Therefore, the time at which the exponential with appropriate scaling decays to 10% of its original value is an upper bound. So we can write, well, I'm going to run out of space here, so I'm going to move over to the next page. I can write that y free response divided by y initial condition is equal to 0.1. That's the time that I want to know. How long does it take to get to that value? To 10% of its initial value. And that, according to the free response equation, is e to the minus zeta omega nt divided by the square root of 1 minus zeta squared. And so this time is a very specific time. I'm going to give it a subscript 10. That's the time at 10%. So what I did is I took that cosine, or it's cosine, right? I took the cosine term and I said, that is bounded. It goes between -1 and +1. It's bounded by this exponential and this factor, 1 minus zeta squared. So this puts an upper bound on the value. Like, so the cosine might be, in the worst case scenario, the cosine is at its peak, right? And that's where it hits this envelope. But it could happen sooner. But this is like the worst case scenario. And that's what I said. It's sufficient to just find an upper bound. So it makes it easy to find the upper bound by just solving this equation. The only thing we don't know is T10. So going through the algebra, we have 0.1 times the square root of 1 minus zeta squared equals e to the minus zeta omega n T10, which, if we take the log of both sides, we get natural log of 0.1 square root 1 minus zeta squared equals negative zeta omega n T10, which finally we can divide through to find T10, which is the expression is -1 over zeta omega n natural log of 0.1 square root 1 minus zeta squared. And what I got when I plugged that in is 0.733 seconds. It's a long time in my world to decay within 10%. So this is why in MRFM we use feedback control to artificially increase the effective damping ratio. Notice that if this creates slow responses to changes because it spends so much time. The book calls it ringing down. It spends a long time ringing down. That's why we want to be, with our detectors, relatively close to 1 with our damping ratio. Instead of 0.0005, that takes a long time to ring down. Or if we're way up high, like damping ratio of 5, way over damped, it takes a long time for it to ooze to the new equilibrium value. So, or to, in this case, free response back to 0. Okay, so that was the example. And I want to move on now to forced response. Whoop.